So in this video, I wanted to go back to electromagnetism for a moment. So on the last video, we went through the force transformations between Frank and Mary, Mary and Frank, and you can see that this fourth component of force is really a power. F dot U is really a power, right? So that would be considered the fourth component of force. Well, let me come back to electromagnetism for a minute. Really, in particular, Coulomb's law. Remember, we said, I think in the second lecture we had, second or third, we had some charge here, say Q1, and we said this thing emanates some electric field, and we called this the source charge, And then out here, we had an electric field, but if we put a separate charge out there, Q2, it felt a force, which we called Coulomb's law. We already knew that force, which was K, Q1, Q2, all over the distance, this R squared. And the force, if these are both positive charges, the force would be trying to repel the two, right? But you'll notice that here's the equation for the force. But you'll notice if this, say this is Frank's frame, if we were to go to Mary's frame, you notice we have to go through a transformation, and the force can't be the same as this. It's been transformed. So not every frame, this Coulomb's law is only good for one frame. It can't be good for all frames right here. Well, what frame is Coulomb's law good for? Well, it's only good when this source charge is at rest. They don't tell you that when you take electromagnetism, but it's really only good when this is at rest. What if this were moving? Well, then I can't use that. So I want to look at some cases where this is moving, and how do we handle Coulomb's law when this is moving? So let's look at the first case right here, case 1. Let's say we have one of the charges here. There's my source charge right here, source. We'll call it Q1. It's at the origin. I'm going to put the other one out here. There's my Q2. Here is some x distance away, except I'm going to say suppose that this charge isn't at rest. Suppose it's moving right here. It's got some velocity v there. And now we ask, what is the force on Q2? We can't use this because this source charge is moving. So how do we handle the force on Q2? So what we can do is suppose we go to Mary's frame. Suppose this was Frank's frame right here, Frank's frame, and so, but now let's switch it over to Mary's frame. So if I draw Mary's frame here, I guess I got to put it in red. Mary's moving this way with a velocity v, so I'll put her right here. So in her frame, this charge right here isn't moving. So this charge, Q1, isn't moving. But what is Q2 doing? Q2 is moving this way at a velocity v. So there's my Q2. And this distance right here, this distance would be x prime, remember, because Mary's measuring it. I can do Coulomb's law on this because the source charge is at rest. Then all I have to do is transform it using the force transformations up to this one. So that's what we want to do. So we're going to look at it from Mary's perspective. I can use Coulomb's law. So this is in red, I'll call it fx prime, well, first of all, fx prime, this is in Mary's frame, we can use Coulomb's law. We can say it's K Q1 Q2 all over x prime squared. We can also say that Fy prime is equal to 0. Mary doesn't see any force in the y direction, so this is 0. We can also get the ux prime, what Mary sees this moving right here, ux prime is just minus v. It's just going this way, and uy prime is 0. So that's what Mary's going to say in this frame. That we can do. Now what we have to do is transform it over to this one. So we just need to use, we want to go from the f primes to the unprimes. So we want to go from the prime to the unprime. So we want to use these two right here. Now you notice here they have an f dot u, f prime dot u prime. Let's first do that. F prime dot u prime. Remember, this is just the dot product. That means fx prime ux prime plus fy prime uy prime. That's all that means. So it really just means this times this plus this times this. There's no z in this problem. Okay, so what does that give me? It just gives me this times this, which is minus v k q1 q2 all over x prime squared. Now I should come back to here and say about time here. And this is in Frank's frame right here. This is going to be at t equals 0. That is, when this is here, this isn't changing, so he could have measured this at any time, but he measured this one at t equals 0, and he measured that one at t equals 0. Well, in Mary's frame, he can measure this one whenever she can measure this one at any time she wants because this isn't moving. She's going to measure the time of that at some t prime, whatever it is. So she'll measure this one at t prime. So this is at t equals t prime. But she has to measure both of these two at the same time because they're moving and you won't get the right distance if you measure their positions at different times. Okay, well, we've got that term right there. Now we can come over here. We've got this term. Now we'll just plug into here. So we got fx equals fx prime. So we got fx is equal to this k q1 q2 all over x prime squared. There's fx prime plus v over c squared times that dot product plus v over c squared times the product, which is this right here, minus v k q1 q2 all over x prime squared divided by 1 minus v ux prime. What ux prime is minus v ux prime. Sorry, it's not 1 minus, it's 1 plus v ux prime, that's minus v all over c squared. Okay, so we got fx is equal to, well, if I factor out, I'm going to factor out the k, the q1, the q2 all over x prime squared, and I'm left with 1 minus v squared over c squared divided by 1 minus v squared over c squared. Well, That's just 1 right there. And now, the only thing is I don't want any primes here, so I need to turn my x prime into x. But we have our equation from right here. X prime is just this right here. So it's x minus, so from right here, x prime is equal to x minus v times t, but t we said was 0, so that's 0, divided by the square root of 1 minus v squared over c squared. What I'm going to do right now is I'm going to, you noticed over here, we called gamma 1 over the square root of 1 minus v squared over c squared, and it was always greater than 1. I'm just going to leave it as gamma instead. So this x prime is just gamma times x. I'm just going to leave it like that. So now I can go back and we can get fx. Fx is equal to k q1 q2 all over gamma squared x squared. Gamma squared x squared. Oh, you notice this is, so what you would have said in electromagnetism, you would have said the force was just k q1 q2 over x squared, but it's not really that. There's an extra gamma squared in the bottom when you're moving. Since this is moving that way, you got an extra gamma squared in the bottom. Since gamma is bigger than 1, fx is getting smaller. So this is smaller than what you would have picked right here. So this is getting, how do I want to write that? It's just getting smaller by this factor 1 over gamma squared. Okay, so if you had the charge moving this way, you can't just use Coulomb's law. There'd have to be an extra gamma squared down in the bottom. Okay, well, that's case 1 right here. Let's look at another case right here. Actually, I want the space here, so I'm just going to say x prime equals gamma x. I'll just leave it there because I want the space right here. And this is smaller. Okay, what happens if instead of being in the x direction, we come back to here? We've got, this is in Frank's coordinate system. We have our q1, except I'm going to put q2 up here at some distance y. And again, this charge is going to be, if this is at rest, we can use Coulomb's law. But if it's moving, we can't. I'm going to have it going this way at some speed v. And now ask, what is the force on that one up there? I didn't calculate Fy on this one, but we know it's probably going to be 0. Why? Because over here, Fy is equal to Fy prime, and we said Fy prime was 0, so if it's 0 times anything, it's 0. So that's why there was no y component of force on this. Okay, now over here, what do? We can't use Coulomb's law, so we have to go over to Mary's frame. From Mary's perspective, right there, from Mary's perspective, x prime, y prime. Now, this charge isn't moving. So this charge is not moving. This charge is just resting there, Q1. And Q2 would be heading off in the other direction. Q2 would be going this way at a speed v. There's my Q2, and this is my y prime. Well, we can use Coulomb's law on this problem, not on that. So we'll find out Coulomb's law here, and then we'll transform it up to here. So let's first get, for this one down here, we can see that the x component, fx prime, is 0. There is no x component. The force is straight up. So fx prime equals 0. Fy prime, we can use Coulomb's law, and that's going to be K Q1 Q2 all over y prime squared. Okay, and then we can get the u x prime, well, the u that is minus v, so ux prime is minus v, and uy prime is 0. Okay, so now we just want to find fx and fy. Okay, remember, we always want to do this dot product first. So f prime dot u prime is just this times this plus this times this. It's the dot product. Well, 0, and you got 0 there, so this term is 0 right there. Okay, so now we're just going to come back in and plug in. Remember, this term is 0 right there. So we just get fx equals fx prime. So we get fx equals fx prime. Well, that's 0. 0. Oh, and the other term is 0 plus 0, so the whole thing is 0. There is no x component of force on this one, which makes sense. Now let's get fy. Well, fy is fy prime, so it's this, k q1 q2 all over y prime squared times, right here, the square root of 1 minus v squared over c squared, square root 1 minus v squared over c squared divided by 1 plus v ux prime over c squared, but ux prime was minus v, so this is just 1 minus v squared over c squared. 1 minus v squared over c squared. Okay, so fy, well, I can get rid of one of these square roots, and that means I only have a square root in the bottom, and that's just as gamma in the top, because gamma is 1 over the square root. So I end up with 1 gamma. I have a k, q1, q2, all over, and then y prime. I need to turn that into unprime. Well, we can see right here, y prime is the same thing. We don't have to, it's just we can get rid of the prime. So this is all over y squared. Well, you noticed over here you had gamma squared in the denominator when it was over here in front of it, but the y, this gamma is in the numerator, so this gets larger. It gets larger right there. Oh, okay, well, what if we were to split the difference? What if we not, here we put it in the x direction, here we put it in the y, let's just put it at some spot out. If we put it out here someplace, so it was like in an xy location right here. And here's your q. And this is going at some velocity v. Well, we can kind of already guess what's going to happen. We could go through this right here, but we know what's it going to do to the x right here. It's going to make the x component smaller, and it's going to make the y component bigger. So normally, if I just draw a line out like this, if there was no, what you would have normally said is just go straight out like this. But we said that it makes this component smaller and this component bigger. So what it's going to do is it's actually going to head up this way, right there. There's the direction of the force. You're going to get both an x and a y component. The x component got a little smaller. The y component got a little bit bigger. So it's going to kind of bend it. And the faster you move, probably the more it would bend it this way. Well, this brings up something that's quite strange. You know, in relativity, we said that you can't send a signal faster than the speed of light. So when you put this, say when this charge, if you just put him right there, this guy doesn't know about it instantaneous. It takes a while for that electric field to get all the way up to there so that one can feel the force. So, when this thing's like this right here, this charge is moving this way, and this electric field is heading out this way right here. By the time this electric field gets all the way out to here, you might say, where is the charge? He's not here anymore. He's moved. Well, he's actually right there. That is, this guy tells you to bend such that when I get to you, you'll be exactly away from where the charge is at that instant. So it's just kind of strange. He almost like knows where you're going to be in the future and says, okay, I'm going to tilt because I know by the time that gets up to here, you'll be here and I'll be exactly opposite the charge right there. If this thing were going faster, I'd have made it out further. This would have been tilted up more right here. Which it's kind of strange that this kind of knows where he's going to be in the future and adjusts the force right there, which is really quite strange. Okay, well, let's go another step right here. Suppose that we had not only this charge moving, but that charge moving. We have them both moving right here. So I'm gonna put. So here we've got this Q1 and a Q2. And this one is moving with a velocity v. And this one will be moving at some other velocity. I'll just call it ux. Okay, now we ask what's going on right here. Well, again, we can't use Coulomb's law unless we go over to Mary's system. So on Mary's, right here, here's Mary's. So now here's one charge, here's the other charge right here, Q1, Q2. I'll assume V is bigger than UX, but it doesn't matter. So here's this would be UX prime, because they were both the same speed, then they'd both be at rest here, but they're not at the same speed. I didn't want to make them the same speed. And this distance would be Y prime. And that distance would have been x prime. Okay, we could get what ux prime is right here because we're just going from this ux to that ux to ux prime, and we've got everything. All the answers to everything are over here. There's my ux prime right there. It's ux minus v. So this is ux minus v all over 1 minus ux v all over c squared. Okay, so there's my ux prime. Okay, so what do I need to do? I need to get my f in the x and f in the y. So on this right here, we can use Coulomb's law. We can see fx prime is 0. There's no x component. It's all in the y. I think I'll do it all in black anyway. Fx prime is equal to 0. Fy prime, well, we've already done that. That's just Coulomb's law. K, Q1, Q2, all over y prime squared. Okay, and we can also get we need to get ux prime. Well, ux prime is just right here. Ux prime is equal to ux minus v all over 1 minus ux v all over c squared. And uy prime, well, there's nothing going up or down, so that's 0. Okay, so now I can do the dot product. The dot product is this times this plus this times this. So f prime dot u prime is equal to 0. Okay, so that makes that term easy. Now we can just, again, we're going to go back, plug in this. Remember, this term is 0 right there. So we need to get both fx and fy. Well, let's first get fx. Fx is equal to fx prime, which is 0, plus v over c squared times the dot product, but that was 0. Oh, so this is just 0. Okay, so there is no x component of force on this one. Now we can get the y, fy. Is fy prime, so it's this, k, q1, q2, all over y prime squared. Again, we're plugging into that fy. We have, plugging it in right to here, we have the square root of 1 minus v squared over c squared. 1 minus v squared over c squared divided by 1 plus vux prime over c squared. 1 plus v over c squared times this. Ux minus v all over 1 minus uxv, 1 minus uxv over c squared. Okay, now what do I want to do? I can get rid of the prime on this because y equals y prime. I think right here, I'm going to put the c squared, v over c squared up in the numerator, and I need to get a common denominator here. So this is k q1 q2, k q1 q2 over y squared. We got that square root, 1 minus v squared over c squared. Okay, so I'm going to, for this, I'm going to put this common denominator over here, so I get a 1 minus uxv over c squared over 1 minus uxv over c squared. 1 minus uxv all over c squared. And that's all going to be over a 1 minus uxv over c squared. That's my common denominator. Then I get a plus vux over c squared plus a vux over c squared. And then I also get a minus v squared over c squared. Minus v squared over c squared. Well, I can see that these two terms drop out. This term and that term drop out. This, I get a 1 minus v squared over c squared. I get a square root of that. I get a square root in the bottom, which just gives me a gamma in the top. So I end up with a gamma k q1 q2 all over y squared, and then that term comes up to the top, which is 1 minus uxv all over c squared. Okay, now let me, I'm just going to distribute this thing through. So this is gamma k q1 q2 all over y squared minus gamma k q1 q2 all over y squared times uxv over c squared. uxv all over c squared. Okay, so this is my new fy right here. So this is my fy. Now, We did this problem almost on the third day when we had both of them moving. You'll notice that when this charge wasn't moving right here, which is what we did over here, we got this right here. So that's just this term right here. So that's the term we got when this wasn't moving. Now with that thing moving in there, we got an extra term in there. Well, what is this other term right here? What is this right here? Well, this other term is just the magnetic force right here. Remember what we said the magnetic force was? We said from back at the very third lecture, we said F was magnetic force was equal to K Q1 Q2 all over Y squared. And then we had some cross products in there. Let me just get the right cross product. We had something like U cross V cross R hat all over C squared. And this is what we had before right there. Well, this is exactly what we have right now because what is this cross product right here? U, well actually it should be V cross U. I got the V cross U. So, no, sorry, we had it right the first time. U and V. What is V cross R hat? V is this way, R hat was this way, so this is out. So that's what this was. This was out. And then U, which is this, cross out, is down, which was negative. That's where this negative came from, right there. So it looks like there's no such thing as a magnetic force. It's just an electric force that's been gone through the transformation. And so you could have derived Biot-Savar's law just from Coulomb's law. All you had to do was apply the force transformation to Coulomb's law, and you get Biot-Savar's law. So there really is no such thing. You could think of it as there's no such thing as a magnetic force. It's just a transformed electric force. Well, what does that say about gravity right here? You know, in gravity, we have the same thing. In gravity, we have a mass, and that's a source mass. And we have some other mass out here, and some R, and there's my, when I want to find the force on, and we use Newton's law of gravity, F due to gravity was G m little m all over R squared. But this can't be true in all frames, because it's a different force when you go to another frame. This is only good when the source charge is at rest, just like Coulomb's law. And so you're going to get the same thing happening in Coulomb's law. So that means if I have a mass and another mass here, and this mass is going this way at some speed v, and this mass is going at some speed ux, and there's some distance y between them, then we're going to get a magnetic gravitational force. They don't ever bring that up in any book, but you would get it. What would it be? Well, it would be exactly like this one, except instead of putting in K, Q1, Q2, you would put in the G, M, big M, little m, right there. And so, and the reason why you would not be able to measure that right here, because first of all, you know, the speed of planets or even masses, they're not that fast. And when you divide it by c squared, it's insignificant. Remember, gamma's around 1. But for charges, you can get charges going very fast, and then you get that's why you notice magnetism in electromagnetism, but you don't notice it in gravity. But it's really there. And so just like before, when you have I think in electromagnetism, you have a charges moving and you get a magnetic field going around. Well, I guess if you had a whole string of masses moving, you'd get a gravitational magnetic field going around. And so it's there. They just don't call it gravitational magnetism. They might call it like frame dragging or something. But that's actually quite strange that you really don't need magnetism. Matter of fact, when you learn electromagnetism in upper division classes, after electric stuff, they teach you relativity, and then they teach you magnetism. Why? Because magnetism is just a relativistic effect. Okay, which is quite strange. Okay.